All right, good morning. This is 11:32 on the Tuesday, the 28th of January 2020. It's supposed to be linear algebra class, but unfortunately I'm the only one in the room. So I'll go on and get started from the current slide, and we'll wait and do announcements until somebody comes in. I saw Dawson up waiting for somebody. May have been waiting for Josh, I don't know, but saw him out in the lobby. Hopefully he'll be coming. All right, we are still in chapter 1, just about to finish it, systems of linear equations, and 1.3 is applications of system of linear equations, and example 5, which is where we're starting today, is going to be analysis of a network. Okay, and I'll draw this diagram that they have. It says set up the system of linear equation that represents the network shown here. So here we have what I call nodes. They may have different names for them. Junctions is what they call them. Let me get my pen set up. Okay, this is junction 1 or node 1. Here is node 2. Here is node 3, here is node 4, or junction 4, and here is junction 5. Okay? Now, they have connectors between these, and junction 2 shows a connection going to junction 1 with a number 20 above it. So, whatever your network here, information, cars, whatever it is moving from 2 to 1 with 20, okay, at a rate of 20. From 1 to 4, we have another pathway, and we don't know what that one is, but we know it's going from 1 to 4, so that's going to be our first variable, x1. Okay? From 1 to 3 is going to be our second variable, and that's going to be x2. Okay, going from 1 to 3. Going from 2 to 3 is yet another variable, and that's going to be our x sub 3. Going from 3 to 4, we know that quantity, that's going to be 10. 3 to 5 is also going to be 10. And 5 to 2 is going to be our x sub 4. And from 4 to 5 is going to be our x sub 5. Okay. Now, some of the information that we have here is that the total, it's basically conservation of whatever you're dealing with, mass, energy, traffic, whatever it is, that everything coming into a node or a junction, the same amount has to leave. Okay? So therefore, and vice versa, the same amount leaving has to be what's coming in. So therefore, if we look at just junction 1 here, you see you got 2 going out, x1 plus x2, and that has to equal what's coming in, that's 20. So here's your first equation. x1 plus x2 is equal to 20. Now the reason I skipped a lot of space there, we've got 3 more variables in there. Okay, so that covers node 1 or junction 1. Let's look at junction 2. Junction 2 says, okay, now you just decide. You can make it any way you want to. I'm going to say that's leaving junction 2 is going to be positive, coming in is going to be negative. It sounds a little backward, but just I like to lead off with a positive number. So I'm going to say actually, I think the best thing to do here is to write it, before I write it over there, write it this way. I'm going to say what's leaving 2 has to be equal to what's coming into 2. And that would be x sub 3 plus 20, that's what's leaving 2, is equal to x sub 4. Okay? So with that in mind, I want the x's on one side and the constants on the other side. So that would be x sub 3. Now for some reason my screen just went black. Okay. And it went black again, and now it says go back. Okay. I don't know what it's doing, but it's doing weird things. Okay. So rewriting this will be x sub 3 minus x sub 3 minus x sub 4 is equal to, okay, what's, if you subtract 20 from both sides, you get minus 20. Okay. Now you could have done it the other way and done minus x sub 3 plus x sub 4 is plus 20. It doesn't matter, okay, as long as you have your signs correct, okay? Now, if you look at node 3 or junction 3 here, again, let's do it the way I said. The sum of what's coming in equals the sum of what's leaving. And that's pretty clear to be x sub 2 is coming in plus x sub 3 coming in. And that has to equal the sum of what's leaving, which is b 20. 10 plus 10 is 20. Okay, I hope I copied it right. Okay. Now, let's go to node 4 or junction 4. The sum of what's coming in, x sub 1 plus 10, is equal to what's going out, x sub 5. So x sub 1 plus 10 is equal to x sub 5. Rearranging that would be an x sub 1 minus x sub 5 is equal to minus 10, because you move the 10 to the other side. And again, you could have done minus x sub 1 plus x sub 5 is equal to plus 10. Doesn't matter. Well, he did decide to show up. Were you waiting on Josh?
No, I was waiting to talk to that UAB.
Oh.
Advisor.
Oh, yeah, it was she over in the corner of the table, yeah. Okay.
Josh is, he's out of town this week.
Oh, is he?
Yeah, they're going to be at a funeral.
Oh, I see, sorry. All right. So let me get things rearranged here. Turn on the projector. Turn on a light. And as promised, when I was talking to the screen, I'll go to the announcements. So UAB was here today, but they probably will also be here in 2 weeks too. But they'll be much more crowded then. Okay, so that's what first thing I was going to say. 2 weeks from tomorrow, Wednesday, February 12th, bunches of universities and colleges will be on the Birmingham West Campus down the B Hall. They'll set up tables all up and down the B Hall, which is the academic building, and from 9:30 to 11:30, Wednesday, 2 weeks from now. And then if they come back, which I hope they will, Thursday the 13th, they'll be here on this campus, 9:30 to 11:30, and that will be this building. They say the campus cafeteria, which I doubt, because it's not that big a cafeteria. To get all these tables in there would take up every eating table, and that's the end of the breakfast time and the beginning of lunchtime. That would be just nuts, I would think. So I believe where they'll be is right next door to that in the faculty staff dining room, which no faculty or staff uses as far as I know. They have several tables in there, and they may spill out into the cafeteria or into the hallway, but I'm guessing that's where they'll be. That's 2 weeks from Thursday, the 13th of February. And then, this is one I've announced before about the power optimization of electrothermal systems, or POETs. this will be at 3 major universities: University of Illinois, University of Arkansas, and Howard University. 10-week internship exposes undergraduate students to academic research in the fields of mechanical, electrical, and material engineering. You're paid $5,000 to go and learn a lot, given free housing, which I think includes free food, and you're given airfare there and back once. So you don't get to come home every weekend unless you pay for it, the others, but they'll pay you one round trip. And it's a great opportunity. That deadline is February 15th. Got all this information, including some websites and things like this, plus the information in this sort of brochure they have. So lots of information there. I encourage you to look into that, because that's a really good deal. All right, now what we were doing was talking about analyzing a network, okay? Here's my network. It doesn't look quite like the one in the book, but all the numbers are the same. And basically, what you do, you look at each, and then the book calls them junctions. I like to call them nodes, whatever you want to call them. Junction probably is a little more standard of a word, but I like node for some reason. And what you do, you look at the inputs and outputs of each location. So let's start with equation 1, with junction 1. And what you have leaving junction 1 is x1 plus x2. What you have coming in is 20, and it has to be balanced, okay? So that means x1 plus x2 is equal to 20. I've tried to leave enough room, may not have, to get all 5 variables in there, because you've got 5 equations from 5 junctions, and so probably going to work best to have 5 unknowns. So go to junction 2, and you've got, and this is what I wrote here. I probably should have written it up there. What you have coming or going out is x of 3 plus 20 is going out is equal to what's coming in, x of 4. So I wrote that down here, x of 3 plus 20 is equal to x of 4. Because over here, I want my matrix set up so that all the variables are on one side, numbers on the other side. We'll subtract x of 4 from both sides and subtract 20 from both sides. So that's what gave me x of 3 minus x of 4 is equal to minus 20. Going down to node or junction 3, what you got coming in is x of 2 plus x of 3. What you got going out is 10 plus 10. So x of 2 plus x of 3 is equal to 20. Coming down to 4, and I just had done this one. What you got coming into 4 is x of 1 plus 10. What you got going out is x of 5. So x of 1 plus 10 is equal to x of 5. But subtracting x of 5 here and subtracting 10, you have x of 1 minus x of 5 is equal to minus 10. Now, frankly, just looking at what's panning out here, I now wish, and I may do it, is flipping the signs here and make this minus x of 1 plus x of 5 is equal to plus 10. Then all you're saying is what you have going out, x of 5 equals what's coming in, x of 1 plus x of 10, so subtract x of 1 from both sides, and that will give you that. Now, the reason I want to do that is I'd rather this be a minus, but it doesn't matter. But I think I will do that just because it will make life easier in the short term, okay? Wait, before I do that, make this a minus, this a plus, and that's a plus. I don't need my eraser at all. Okay, so that gives you 4 equations. The 5th equation will relate to junction 5. You tell me what's true about junction 5. An equation that represents what's going on at junction 5. What you got going out? Second? No, that's coming in. Going out is, you could start with 10 if you wanted to, but just looking at this going out, is x of 4, and that equals to what's coming in, which is x of 5 plus 10, right? Because that's coming in also, if I copied it right, and I think I did. So that's what we want to be true. So what I'm going to do is subtract x of 5 from both sides, and my last equation will be x of 4 minus x of 5 is equal to 10. Okay, there's my system of equations. Okay, now what do you think we're going to do next?
Solve for each one.
Okay, how do you recommend I do that? What technique?
I forgot what it's called.
Okay, I would probably first write it as a matrix. Isn't that what we've been doing? Okay, what would the matrix be? Now I'm going to get rid of some stuff here because I have written too big and taken up too much room. So let's write down here what my matrix is. All right, tell me. One, 0, 0, no, 0, 3, 5 variables. Okay, and then 20. Okay. Most important, as sloppy as mine looks, that you keep it lined up. Okay? Second, 0, 0, 1, negative 1, 0, negative 20. Good. Next. Zero, 1, 1, 0, 0, 20. Next. Negative 1, 0, 0, 0, 1, 10. Okay, and last. 0, 0, 0, 1, negative 1, 10. All right. Now, typically with a matrix like this, what's the first thing you want to happen? Upper and upper left, we got it. Good. Okay, so next, what do we want? Zeros below it. We got 3 zeros below it, but one that's not. How can we get that negative 1 to become a 0? Row 1 plus row 3 is the new row 3. I mean, row 4 is the new row 4. Row 1 plus row 4 is the new row 4. Okay, so that is going to become this matrix. You're using the first row, so write it down. 1, 1, 0, 0, 0, 20. Okay? You're not messing with row 2 yet, so leave it alone. 0, 0, 1, minus 1, 0, negative 20. Okay? All right, next. Not messing with row 3 yet. Write it down. 0, 1, 1, 0, 0, 20. Okay? We are messing with row 4. What does it become? 0, 1, 0, 0, 1, 30. Not messing with row 5, so write it down. 0, 0, 0. 1 minus 1, 10. Okay. Now, just a quick recap. You wanted a 1 here, we had it. You wanted zeros below, we got it. What's the next thing we want?
After that first zero,
You have 1 and 1. We don't have 1. So what do we do to make 1 happen there?
you could add either row 3 or row 4.
To row 2, and that would certainly do it. Or, can you think of another option or two? Flip. Okay? Either one will work. Since one involves adding and one just involves writing, I'm tending to go with the lazy part, okay? The writing part. But which one do you want to flip? But if you want to add, we'll add. You choose. It's
Row 2.
okay. So row 2 and row 3, I'm going to just give them that kind of symbol, flipping them. All right. So we're not using row 1, so we're going to write it down. 1, 1, 0, 0, 0, 20. We're flipping row 2 and 3, so let row 3 and row 2 place. That would be what? Okay, wait. We'll flip, yeah, 1, 1, 0, 0, 20. Okay? And okay. And we're not messing with 4 or 5, so just write them down. 0, 1, 0, 0, 1, 30. And 0, 0, 0, 1, minus 1, 10. All right. So, again, a recap. We wanted a 1 there, we had it. 0's below it, we got it. We wanted a 1 here, we got it. Now what?
I'm going to leave coefficient of 3, the third one to be 1, so we already have that. So then in row 4, you want to get rid of that 1 under.
Right. And probably also that we're going to do Gauss Jordan. So all we have to do is read across all the fractions. Okay? So, are you okay with that? All right. So, what are we going to do to make that 1 become a 0? Now, I need someplace else to write. And I think I'll erase my equations there because we've already used them and I don't think we'll need them again. So it's okay for me to erase them. I was going to erase my network, but we may want to look at that at the end. Okay. Okay, now what I think I heard you say is negative row 2 plus row 1 is the new row 1. Is that right? All right. So that's coming up here now. All right, so do it to it. Minus row 2 plus row 1. 1, 0. Excellent. That's what we wanted. Negative 1, 0, 0, 0. Ooh. All right. Now, okay. We're using row 2, so let's just write that down. 0, 1, 1, 0, 0, 20. Okay? Now, row 3 is fine, so we're going as far as column 2 goes. So we'll write it down. 0, 0, 1, minus 1, 0, minus 20. Okay? Yes, sir. How about row 4? I think you mentioned that one. One, and what? How do you do that? Negative row 2 plus row 4 is the new row 4. Okay, you do it to it. 0, 0, negative 1, 0, 1, 10. Okay. Getting crazy looking at all these rows that look so similar. And the 5th row is fine as far as column 2 goes, so we'll write it down. 0, 0, 0, 1, minus 1, 10. Okay. So, quick recap. I'm going to say very quickly, but let's try it. Okay, you wanted a 1 here, 0 is below it, got it. You wanted a 1 here, 0 is above and below, got it. What's the next thing you want?
And row 4, you want the...
Actually, yeah, you want a 1 there, you got it. Okay, so now what? First non-zero entry in 3, and you want 1 space over from 2. You want that to be a 1. That's already a 1. Fantastic. Now what?
Now row 4, you want to have we'll make that everyone 0 and have it 1.
And now you want a 0 there.
Yeah, 0 there.
You want a 0 there. Oh, you're talking about over here?
Yeah.
That's right. Those fall where they lie. Don't worry about them yet. Take care of column at a time. So actually, I also want a 0 up here, here, and there. That one's already a 0, so we're fine. So we got 3 to fiddle with, because I want to have reduced row echelon form. Gauss Jordan elimination. Because I'm really lazy, I just want to read the answers off the top. Okay. Now, I know right now that row 1, the value here is going to be exactly the same as the value here because of that. But that's beside the point. Let's go. We're going to get rid of that minus 1 anyway. Okay, how do we do that? I'm going to put row 3 plus row 1 is the new row 1. Yeah, it doesn't matter. It says the same thing. Okay, so I'm going to try to squeeze it in here. Come on. Okay. All right. So row 3 plus row 1, what does that give us? 1, 0, 0, negative 1, 0, negative 20. All right. I hope I did it right. Now, row 2, we also need to change that. So what will we do? Actually, that will work. You had to look back here and make sure nothing is going to mess with there, but that's going to be fine. So let's do it. Row 4 plus row 2 is going to be the new row 2. Okay? So do it to it. 0, 1, 0, 0, 1, whoa, wait, have I missed one? No, we got our 5. I hope they did it right. 0, 1, 0, 0, 1. So last column. 30. Perfect. Okay. Now, we're using row 3, so we just write it down. 0, 0, 1, minus 1, 0, negative 20. Okay. Now, we need something to change in row 4, and what's that? Not quite. You want it to be a... Yeah, you want it to be a 0. How do you make it a 0? Row 3 plus row 4? Perfect. Row 3 plus row 4 is the new row 4. Doesn't matter which order you add them. So what do you get? 0, 0. Oh, okay, 0, negative 1, 1, negative 10. Okay, and row 5, as far as we're dealing with column 4 now, column 3 now, it's perfectly fine, so just write it down. 0, 0, 0, 1, minus 1, 10. Okay. Now, quick recap. We wanted a 1 there, 0 is below, got it. 1 here, 0 is above and below, got it. 1 here, 0 is above and below, got it. What's the next thing we want?
Row 4.
Yep.
Column 4.
Row 4, column 4?
Yeah.
Nope. Or positive 1. So that's pretty easy to change, isn't it? Just multiply everything by minus 1. Or divide everything by minus 1 if you prefer that. So this becomes a plus minus plus. I hope you're okay with me doing it that way. I'm being very lazy and not wanting to write everything down. Okay. Another thing you could have done was exchange row 1 and 2. I mean 4 and 5. But that does create an issue here, doesn't it? Yes, it does. Okay. Not a bad issue, but an issue. What do you notice? And you don't have to notice it yet. I just wondered if you did. Okay, forget that. What's the next thing you want to happen? Okay? As I said, you wanted a 1 here, 0 is below, you got it. 1 here, 0 is above and below, you got it. 1 here, 0 is above and below. Something like that. Then you wanted a positive 1 there, you got it. What you want to happen next? Yeah, you want a 0 here, a 0 there, that's already a 0, and a 0 there. So how do we make that first negative 1 become a 0? I'm going to have to erase some stuff. Now, just have a question for you. Would you rather I snake around and do right to left, or start over here and go left to right? I don't really care. Okay, so wipe out this one and go this way, or come down here. I don't care. What's that? Okay. What I'm going to do, I'm going to wipe out the whole bottom row, hoping that we haven't made any errors. If we have, it's up to you. No, I mean, it's your fault. I mean, it takes a while when you got so much on the screen for it to pick up. It's not doing anything now, and that's disconcerting. Let's see if when I stop, things start disappearing. Yes, they do. Okay. All right. Now, still doesn't matter to you. Okay. I thought you said left to right first, so I'll do it. Okay. Now, what we're going to be doing is using row 4 to eliminate the -1 in row 1. I think what you said, or did you say, row 4 plus row 1 is the new row 1. All right, so let's write that new row 1 down. Help me. 1, 0, 0, 0, -1, -10. Okay. Now, row 2, as far as column 4 goes, is hunky-dory, so just write it down. 0, 1, 0, 0, 130. Okay. What do we want to happen in row 3? Okay, the -1 becomes 0. How do we make it happen? Row 4 plus row 3, I wrote it down backward the other way, but that's okay, is the new row 3. Okay, so what does that become? 0, 0, 1, 0, -1, -10. All right, next we're using row 4. That's the leading one we're dealing with, so we're going to write it down. 0, 0, 0, 1, -1, 10. Okay. What's the next thing we want to happen? Okay, in row 5? Yeah, okay, that 1 becomes 0. How do you make that happen? Yep, that'll do it. Okay. So, what will that new row 5 be? 0, 0, 0, 0, 0. 0. Say again?
So that means it's infinite amount of,
I can't read.
so whenever there's a row of zeros, does that mean it's infinite?
No, okay, that means infinite number of solutions. You're absolutely right. But you want that row of 0 to be at the bottom. It is at the bottom. So that's good too. And what I thought maybe you would notice here, these two rows.
Yeah, I did. Actually, you talked about it.
Yeah, yeah, and that's what guaranteed that was going to happen. Now, if this had come out all these zeros, would that be a 10? What would that mean?
No solution.
Yes, no solution. This system will not work. There is no way to make it work. This says there's an infinite number of ways to make it work. And we got to determine that. So we're basically there, aren't we? What do we do from here?
The values.
Okay. Well, sort of the first thing we're going to see, what these leading ones tell us, we can now define x of 1, x of 2, x of 3, and x of 4. Don't have a leading one for x of 5, so therefore it becomes a parameter. Okay. Now, what value do you want to assign it? T. All right. T for 2. Okay. So let x of 5 equal the parameter t. Okay? Then, what can you say? Start with x of 1. X of 1 Okay, now remember this is t. It'd be if you're writing across now, and this is where the way I used to do it would be a little helpful here. But remembering where this was x of 1, x of 2, x of 3, x of 4. Yes, ma'am. My office hours a day are 12:45 to 1:15. Right, yeah. Do you want to do it? Do you want to start them now? Yeah. Let me pause this for a moment. Do you mind? Okay. If you want. Okay.
So x of 1 would be negative 10 plus t.
Yes, you could do it that way. I tend to like to say, yeah, I'd like to say t minus 10, but it doesn't matter. Okay, that says the same thing. And x of 2, 30 minus t, and x of 3, minus 10 plus t or t minus 10. Doesn't matter which way you do it, but it's just like 1. Okay? Yeah, t plus 10. And x of 5 is equal to t. So if you wrote that as a quintuple, I guess you would say, that would be, and you don't have to, but you could write it t minus 10, comma, 30 minus t, comma, 10 minus t minus 10, yuck, comma, t plus 10, comma, t. All right. And then you pick any value for t and go with it. I think I would like the t to be 20. Now, I chose it out of the wild sky. So if t is equal to 20, this would be 10, 10, 10, 30, and 20. That would work. Okay? If you choose t equal to, I don't know if if you choose t equal to 0, that means you put the x1 in the wrong direction. You should have it going up, because then x1 would be negative 10. You just change the arrow on it, because usually you want these to be, it would just mean it wouldn't be leaving, it would be going into 1. So that's why I chose t equals something that wasn't going to make it. Now, if t was equal to 10, x of 1 is 0, x of 2 is 20, x of 3 is 0, and x of 4 is 20, and then 10. So that would work too, no problem. Any value you choose for t, it will work. It doesn't have to be a multiple of 10 either. I was just using them because they gave us 10s in the other ones. You can use 1, you can use, that depends on what you're dealing with. If you're dealing with cars going through intersections or something like that, then you probably would want to use 3.5, because you don't have 3.5 cars, So if it's something that needs to be an integer, then use integers. But it doesn't matter if they're negative. That just means that variable should be going that way or this way or whatever. It just would accommodate those. And it could be the x of 5 was 0, and if it was, then you have nothing happening here, and you just have a system of those. That should be your new network. So, all right. Let's see if we got the same thing they did. X of 1 is t minus 10. X of 2 is 30 minus t. They did minus t plus 30. X of 3 is t minus 10. X of 4 is t plus 10. And x of 5 t. Yeah, infinitely many solutions. So there's many ways that could run. They chose x of 5 equal 10 and wound up with 0 for x of 1 and 0 for x of 3, okay, which is fine. Now, the reason I did that one first, we didn't do the polynomial ones, which tend to be a little involved, and I wanted to move on. But I knew you were going to hit this if you haven't already. Kirchhoff's laws? No, in E&M physics, electricity and magnetism. You're going to get there, so that's what I wanted to do. But this one helps get us ready for that. It's not the same. All right, to erase? Okay. And by the way, Kirchhoff could be a legitimate paper topic now. It's a physics thing, but it's mentioned here. So or Kirchhoff's laws, how do you come up with them? Or how do you apply them? There's lots of things you could use there. But they mentioned here, you may be able to see how the network I just erased could be flow of traffic through the streets of a city, flow of water through an irrigation system. But here is another, this is electrical network. It has a little bit of a variation here. The analysis of such a system uses two properties of electrical networks known as Kirchhoff's law. And the first one was what we were using before. All the current flowing into a junction must flow out of a junction. That's what we use. That's all we use on that first one. The second one, though, is and that's basically a conservation of charge, by the way, when you get to it in physics. The second one is the sum of the products, okay, IR, And have you gotten that far yet? V is equal to IR? Ohm's law? Have you gotten there in physics yet? Maybe not. Okay, you're probably still in electrical forces and fields and stuff. Is that right?
We're like thermodynamics right now.
Oh, okay, okay. Y'all starting with thermodynamics. We'll get to E&M later. Okay, all right. So basically what we have, the other, is kind of like conservation of voltage, okay? They don't usually say it that way, but that's what it turns out to. The sum of the products of your voltages around a closed path, okay, what they're saying, the sum of the products, the voltage drops has to equal to the voltage sources in any closed path, which if you don't say it that way, the sum of the voltages around that has to equal 0. Works out the same thing. Now, just a little bit of nomenclature here. Current is measured in the unit called amperes, and its symbol is capital A because Ampere was a person's name. This is current. And current, by the way, is charge per unit time rate of change of charge. Okay? Resistance, that's measured in ohms. What a weird symbol that is. Anyone know? Do you know what that is?
Omega?
Yeah, it's a capital omega. Now, why a capital letter there anyway? Well, ohm is named after Georg Friedrich, I think, or something like that. Ohm. So, why didn't they use capital O to represent ohms?
Capital O is oxygen.
Say again?
Capital O is oxygen.
Capital O is what?
Oxygen.
Oh, no, okay, well, it is, but that's, oxygen is chemistry. We're in physics. Yeah, we don't care about physics. I mean, capital A might be americium, but it's not. It's AM, you know. What if you had 5 ohms and you use capital O as, it looks like a 50, so we don't want to use capital O. So we went to the Greek alphabet. But the Greek letter corresponding to our O in our alphabet is Omicron. And capital Omicron looks just like a capital O, so it didn't get any better. The Greek alphabet, unlike the English alphabet, has 2 O words. Omicron corresponds to our O, but their very last letter in their alphabet is omega, which spelled starts with O, but it has this symbol. So that's why we use that. Don't know if we have time for a dumb story or not. So anyway, this one isn't quite so dumb. In the Greek alphabet, the first letter is
Alpha.
And the last letter,
Omega.
have you ever heard of alpha, omega? Beginning and the end, exactly. That's exactly there. So it's not that Omicron in the middle or south of the middle, it's the very end. Okay, now, dumb story? All right. Physicists are very creative and a little wacko. Okay. The resistance is the resistance to charge flow. But there's another concept in physics that is that ease at which charges flow. And that's called conductance, how easily charges conduct. And the definition for conductance is 1 over resistance. Okay? That's it. I mean, 1 over resistance. Now, resistance is measured in ohms, named after Georg Friedrich Ohm, or whatever his middle name was. What are we going to name the unit of conductance? I don't know who came up with it, and they didn't seem to want to honor him if there was somebody who did anyway. So they have to have a unit for conductance. Anyone, you want to make a guess of what they used? They used a mode. Okay? Now, not because it was discovered by Larry and Curly's friend. That's not the issue. Okay? How did they come up with mode? A conductance is the reciprocal of resistance. You spelled it backwards, Art. This is nuts, or clever. Now, what unit will they use? Okay, well, number one, it doesn't need to be capitalized. It's just a MOH, okay, MHO, I'm sorry, MHO. Well, we already got M for meter, so we can't use little m. Capital M is mega, so we really don't want to use that. What symbol will you use for a mode, which is the unit for conductance? Second? I'm serious. They just reciprocated an omega and made it that. That's no symbol in the world, okay? There is no letter that has that as a symbol. They just flipped it over.
Very artistic.
Huh?
It's very artistic.
Yes, so isn't it? Okay. So, anyway, we're not dealing with this, though, so let me erase those. That was just basically a waste of time. No, I still find it interesting. Okay. Now, and by the way, since we are mentioning other things like this, since you haven't gotten there in physics, the Ohm's law, Ohm discovered resistance or defined it and stuff. His law says that, and for some reason my pen's not, there it is, okay. Ohm's law states that, and you can use the symbols any way you want to. How do they do it in the book? I don't see they use it at all. You'll see it sometimes written as E is equal to IR, where E is electromotive force or voltage, or you can actually do V is equal to IR, and that stands for voltage. Okay, so those are the same. E and V mean the same. Okay, so a battery source or any other source of voltage is E or V, whichever you want to call it, and then your current, oh, I didn't mention that. The symbol for current is I, the symbol for resistance is R. These are your parameters. Your units are A and omega, but the thing. Now, the symbol for voltage is either E or V, but the unit is also V, capital V, because it was named after Alessandro Volta, a Italian who did some of the early work with batteries and stuff. So anyway, that's what it is. Now, let me also represent how you do these on diagrams. Okay, a battery, which is E or V, is represented by a long line, short line, or it could be a short line, long line. What this indicates, this is the positive side of the battery, that's the negative side of the battery. Now, you could have multiple cells, so you could do a series of long, short, but at one end is going to be a short, the other end a long. That means you have an increase of voltage going in that direction. If you happen to be going in the opposite direction, that would be a negative voltage, okay, because you're going down in voltage. Now, your resistors are represented like this. Okay, that's the symbol for a resistor. Okay, usually you'll have an R by that indicating it is a resistor. And usually on your current here, in your circuit here, you'll have an arrow in one direction or another. It's telling you that's your current. And if you're going in this way, you have a voltage drop minus IR, because you're going down in voltage. Anytime current goes through a resistor, it loses potential, so it's going down. Now, if you're going backwards there, that would be a rise in a plus IR. Okay, so that's just a little bit of the nomenclature here. You don't need to know all that, but some of it you probably would. So let's hit it. Here you're going to do analysis of an electrical network. Okay? What we have here is one node here, or junction here. Okay? And you have a wire coming into it, hitting a resistor here. We're going to call R1 of 3 ohms. Then you're going to hit a battery here, and they show the plus side here, minus side here. I like to make mine a little bigger than they do in the book. Okay? Coming also in or leaving one from your first junction is another resistor, and this will name R2. R2 is 2 ohms. Okay? And it just goes over here to your second junction 2. Okay? Also, either coming or leaving from junction 1 is another line with another resistor here, R3. And this resistor happens to be 4 ohms. Okay? And it runs into a battery, plus side to the left. Oh, and this battery up here was 7 volts. Okay? And the battery down here is 8 volts. Okay? And that then connects to junction 2. All right. Now, I think I've got everything listed. Now, I'll talk about paths in a minute, okay? But let's first talk about, I guess we need to talk about paths too. But remember, Kirchhoff has 2 laws. The first being, oh, I did leave off 3 things. This, they're saying, is current I1, this is current I2, and this, sorry about that. This is current I1. Now that makes sense because you have the positive pole of the battery here, and that means it pushes the current this way. Now when you get the physics up to it in physics, you'll also learn there's sort of a discrepancy. Everything in physics always goes from high potential to low potential. Okay? Everything. Heat, everything. Okay? However, current, especially direct current like this, that's what batteries indicate. Since it's electrons moving, they move in the opposite direction because they're negatively charged. That's an issue. But we still say the current, most of the time the current is the movement of positive charge if we had a positive charge. Okay, so we're going to use that convention. It's called the conventional current as opposed to the electron flow. Okay, so I2 we're going to have going that way, and I3 down here we're going to put in that direction, again because the battery is indicating it's pushing it that way. Okay, now with that in mind, then we can ultimately talk about Kirchhoff's law. Now, you can always make more equations than you need, and you probably will, okay? The junction law says that the total, and remember, its charges or current coming into a junction equals that going out. So coming into R1 to junction 1, you got plus I3 minus I2 plus I1 minus I2 plus I3 will have to equal 0. Because this current is coming in, this current is leaving, this current is coming in. Okay? The way I've drawn it. Okay? If you go to junction 2, you got leaving junction 2 is I1. coming in as I2 and leaving as I3, well, guess what? Those are the same equations. They're just opposite of each other. So that only gave you one equation. But quite often, if you have multiple junctions here, you can do an equation for each junction. This one just doesn't give you anything. Okay? Now, we have three unknowns here, so we need at least three independent equations. These two are basically the same equation. So you still need two more. Use one of them, but the other is just redundant. Okay? So here's where we use the loop law, is what they call it. They call it closed paths. In physics, they often call it loops or closed paths. Okay. You can draw any closed path you want. One might be the one that goes around the whole circuit here. Or it could be one that goes around this loop here. That's the one the book uses. And the second being one that goes here. One that goes here. That's the one the book uses. Okay. So since the book is using these two, let's just use those two. They work well, but you could have used the one all the way around. So here's, and I call it the loop law, the total voltage drop around any closed path is 0. Okay? And since we indicate our currents this way, it sort of makes sense to indicate the flow in that direction. Otherwise, you have to negate everything. Okay? So, now remember, these are your three variables here. Okay? Everything else you have numbers for. So let's talk in terms of the current. And now you'll get to this in physics also. Just because you have a resistor here, it doesn't affect the current at all. Because conservation of charge, the same charge coming into a resistor has a leak. What you're losing here is the energy, which is your voltage. The energy of those charges. And you'll get this in physics, that voltage is joules per coulomb, energy per unit charge. Okay? So that's what you're losing, energy. You're not losing charge. The same charges have to go. Like conservation of mass, it's just conservation of charge. Okay? So, what you're measuring is current. So I1 minus I2 plus I3 has to be 0. Because the total current coming into a node is 0, or the same coming in has equal way out. So you could say I1 plus I3 is equal to I2. But since I want all my currents to be my unknowns, I'm going to say I1, now do they call it capital I? Yeah, they do. I1 minus I2 plus I3 is equal to 0. Okay, that's the loop law. I mean the junction law. Now, if you tried to do number 2, you would have minus I1 plus I2 minus I3 was equal to 0. That would be the same equation, just with minus, opposite signs. So that doesn't give us anything. So let's do our closed path. Now, you just pick a point. I'm going to pick this one right here. Okay? We're out of time. Goodness, great. Yeah, that's right. I did have to go down and get a thing. So we'll pick up right here. We set it up. Just reminding me, I've already set it up, and we'll pick it up and go from there. Let's see if we did enough to get any homework exercises. I hope so. We aren't doing polynomial curve fitting, but if you want to do any of the odds 1 through 13, you certainly could. 15 is about the same. 17, 19, any of those you want to. Now, you can do number 21, okay, and or 23. Hold off on 25 because we didn't finish Kirchhoff's. Okay, so new things you could do would be 21, 23 or 21 or 23. You can do any of the other odds before that if you want to try them. That's up to you. All right. Thanks for watching.